Your air conditioner was never designed for the humidity levels most Americans live with. And because of that gap, 60% of its energy goes to fighting moisture instead of cooling your home. Builders in the ancient city of Mohenjo-Daro solved this 4,000 years ago with salt water and buried clay pipes that kept interiors dry and comfortable through monsoons that would drown any modern HVAC system. By the end of this, you will understand exactly why this technology was banned in America and how to build it yourself. Right now, in Houston, Miami, New Orleans, and Singapore, millions of air conditioning compressors are running at full capacity. Not because the homes they serve are hot, because the homes they serve are wet. This is the secret the HVAC industry never advertises. Your air conditioner was designed to lower temperature. That is called sensible cooling. But in humid climates, 60% of the energy your unit consumes goes towards something else entirely. It goes toward wringing water out of the air. Engineers call this the latent load. Your compressor handles it by overcooling air far below the temperature you actually want, forcing moisture to condense on freezing cold coils, and then sometimes reheating that air before it reaches your living room. It is the most inefficient thermodynamic process in your entire house. Engineers describe air using something called a psychrometric chart. Temperature runs along one axis, and moisture content runs along the other. Human comfort sits in a narrow band. That band is 72 to 76 degrees Fahrenheit at 40 to 60% relative humidity. Standard vapor compression air conditioning can only travel one path on that chart. It must cool in order to dehumidify, and it cannot separate the two tasks. This is not a flaw that a better compressor can fix. It is a fundamental thermodynamic constraint of the refrigeration cycle itself. Walk through neighborhoods in Galveston, Texas, in Baton Rouge, Louisiana, and in Manila, Philippines. You will see air conditioning units running 12 to 16 hours a day. You will see electric bills climbing past $300 a month. You will see mold crawling behind furniture and inside wall cavities. You will see dust mites thriving in trapped moisture. Indoor air quality is collapsing even though the machine that is supposed to fix everything runs without stopping. Families are paying more money every year for a system that cannot solve the problem it was sold to solve. But here is what changes everything. Cooling and dehumidification are not the same problem. They require completely different physics. And 4,000 years ago, engineers on 3 continents already knew this. In the Thar Desert of Western India, temperatures reach 120 degrees Fahrenheit. Humidity during monsoon season climbs past 90%. Modern engineers would call this an impossible cooling challenge. Ancient builders called it normal life. Beginning in the 3rd century, architects across Rajasthan and Gujarat constructed elaborate subterranean structures, known as stepwells. These played a significant role in defining subterranean architecture in Western India for over 1,000 years. The most famous is Chand Bowery in the village of Abhaneri. Built during the 8th and 9th centuries, it plunges 13 stories into the earth. 3,500 steps descend into darkness. Tourists photograph it for its geometric beauty. Engineers study it for something else entirely. Temperatures at the bottom of Chand Bowery run 5 to 6 degrees Celsius lower than at the surface. That difference matters. But the real engineering insight is what the water itself was doing. The massive surface area of exposed groundwater acted as a humidity buffer in the chambers and galleries carved into the surrounding stone. Air circulated past cool rock and water surfaces that moderated both temperature and moisture at the same time. These were not merely wells. They were passive climate control systems that separated sensible and latent cooling using nothing but physics and stone. Then, during British colonial rule beginning in 1858, officials declared stepwells unhygienic. They called them breeding grounds for disease. Hundreds were filled in, sealed, or demolished across the subcontinent. An entire architecture of passive cooling was erased in the name of sanitation. The real engineering knowledge these structures contained was never studied, never preserved, never replaced. 5,000 miles west, in what is now central Iran, Persian engineers had discovered the same principles independently. The qanats of Yazd stretched for miles underground, carrying water from distant mountain aquifers. But they served a dual purpose that modern archaeologists only recently understood. Air flowing through miles of underground channels did not just cool down, it dried out. Moisture condensed on the cool tunnel walls. Mineral deposits lining those walls, rich in calcium compounds, absorbed additional moisture from the passing air. The Persians had built desiccant dehumidifiers beneath the desert without ever using that word. At the far end of those qanats, cooled and dried air fed into yak-chal chambers. These ice houses had walls 6 feet thick, made from a mixture of sand, clay, lime, goat hair, and egg whites. Archaeological teams with modern monitoring equipment have measured temperatures inside these structures, holding at 25 to 30 degrees Fahrenheit through summers exceeding 115 degrees Fahrenheit outside. They stored ice in the desert for an entire civilization, using nothing but physics. In Egypt, the principle appeared again. Natron, a natural mineral blend of sodium carbonate and sodium bicarbonate, served not only for mummification, but for climate control. Underground storage chambers beneath temple complexes at Dendera show air passages routed over beds of natron before reaching food stores and living quarters. The natron stripped moisture from the incoming air. This is a desiccant dehumidifier. Egyptian builders were constructing them 3,000 years before anyone coined the term. Along the humid Malabar coast of Kerala in southern India, traditional Nalukedu houses incorporated lime plaster walls embedded with sea salt compounds that absorbed excess moisture during monsoon season and released it during drier months. Measurements at restored heritage structures show interior humidity holding between 55 and 65% when exterior conditions reach 95 to 100% relative humidity. The buildings breathed. They self-regulated. No electricity, no compressor, no refrigerant, just materials that understood moisture. Every civilization that mastered hot and humid climates discovered the same two-part answer independently. Use the earth for cooling, use minerals for drying. Persians, Indians, Egyptians. 5,000 years of convergent engineering across 3 continents. Then, in less than 1 century, both halves of that elegant solution were replaced by a single machine that does both jobs poorly. To understand why the ancient solution works so well, you need to understand 2 separate physical processes. Your air conditioner pretends are one. Sensible heat is the heat you feel. It is what a thermometer measures. Moving air from 95 degrees Fahrenheit to 75 degrees Fahrenheit is sensible cooling. The earth beneath your home, from 6 to 10 feet deep, holds steady at your region's annual mean temperature. In Chicago, that means 55 degrees Fahrenheit year-round. In Atlanta, 62 degrees Fahrenheit. In Houston, 68 degrees Fahrenheit. That temperature does not shift more than 1 or 2 degrees across the entire year. Circulating water through pipes buried at that depth and then running it through radiant panels or a fan coil unit indoors handles sensible cooling with almost no energy. A small circulation pump from 50 to 150 watts. That is all. Latent heat is entirely different. Latent heat is the energy locked inside water vapor. Converting humid air at 80% relative humidity down to comfortable air at 50% releases enormous thermal energy. In tropical and subtropical climates, the latent load actually exceeds the sensible load. Your air conditioner handles this worse than anything else it does. The compressor overcools air to force condensation. It wastes energy reheating that overcooled air. It cycles on and off, because moisture levels fluctuate independently of temperature. The machine was designed to make air colder. Drying the air is an expensive, wasteful side effect. When you separate these 2 tasks, something elegant happens. Each can be handled by a technology specifically optimized for that single job. Ground-coupled water loops achieve coefficients of performance approaching 20 to 30 for passive circulation because no compressor is involved. Desiccant materials excel at stripping moisture using only low-grade heat. Regeneration temperatures can be as low as 60 degrees Celsius. A basic flat-plate solar collector provides more than enough. The National Renewable Energy Laboratory has identified this separation of sensible and latent loads as capable of reducing total residential electricity demand by 25% or more in humid regions. 2 problems, 2 solutions, each one brilliant at its specific task. The ancient world always treated these as 2 separate problems. Modern engineering rediscovered this in the 1930s. And then something remarkable happened. The solution was built, tested, proven, and then systematically buried. The closed-loop hydraulic half of this system is beautifully straightforward. High-density polyethylene pipe, 200 to 300 millimeters in diameter, buried in horizontal trenches at 6 to 8 feet deep. or installed vertically in boreholes reaching 100 to 400 feet down. A mixture of water and antifreeze circulates continuously through these buried pipes. As the fluid travels underground, it sheds the heat it collected from the building into the earth as constant thermal mass. The water returns cooled and flows through radiant ceiling panels, chilled beams, or a simple fan coil unit indoors. No compressor, no refrigerant, no phase change. Just water carrying heat from your living room into the ground. The circulation pump draws 50 to 150 watts, less than a reading lamp. The ground loop itself lasts more than 50 years with zero maintenance. The first successful commercial ground source heat pump was installed in 1946 at the Commonwealth Building in Portland, Oregon. Nearly 80 years of proven technology sitting in plain sight. The Department of Energy confirms these systems use 25 to 50% less electricity than conventional heating or cooling. Indoor components last up to 24 years. The ground loop outlasts the building it serves. The desiccant wheel half is equally elegant. Picture a slowly rotating wheel about the size of a car tire. It is made of a honeycomb matrix impregnated with silica gel, zeolite, or lithium chloride. It turns at 8 to 20 revolutions per minute. On one side, humid outdoor air passes through the honeycomb. The desiccant material captures the moisture and holds it. Dry air exits and enters the building. On the opposite side, heated air passes through the same wheel, moving in the other direction. That heat drives the absorbed moisture out of the desiccant and exhausts it outdoors. The wheel keeps turning. The drying never stops. The regeneration heat required is modest, 60 to 80 degrees Celsius. A flat plate solar thermal collector, the simplest and cheapest solar technology, provides this easily from 4 to 6 square meters of collector area on your roof. The small motor that turns the wheel draws under 20 watts. This is truly solar-driven regeneration. Now put the two halves together. The desiccant wheel strips moisture from incoming ventilation air. The hydronic loop cools the building structure through radiant surfaces. The two systems share no fluid and no air path. They operate completely independently, yet they complement each other perfectly. The ground loop never has to deal with moisture, so there is no condensation risk on cooling surfaces. The desiccant wheel never has to cool the air, so it can focus entirely on drying. Each system does exactly one job and does it brilliantly. Total continuous electrical draw for the combined system is 100 to 250 watts. Compare that to a conventional 3-ton air conditioning unit pulling 3,000 to 3,500 watts from your electrical panel. Field research supports these claims. In tropical Malaysia, 2-stage solar desiccant cooling systems delivered 27.9% to 33.9% energy savings compared to conventional air conditioning. Studies across 6 major Colombian cities demonstrated electrical power savings of 52 to 60.9% in every climate zone tested. A desiccant system installed at a hotel in Taoyuan, Taiwan, confirmed effective humidity control year-round, using rejected heat from existing equipment to regenerate the wheel. Published research documented up to 64.3% increase in coefficient of performance when desiccant wheels were integrated into building climate systems. It describes a system that uses 200 watts instead of 3,000 watts, that runs on sunlight and earth temperature, and that handles 100% humidity without breaking a sweat. So why has no one ever told you about this? In 1902, a young engineer named Willis Carrier stood in a Pittsburgh printing plant solving a humidity problem for a publishing company. His invention became the foundation of mechanical cooling. By the 1920s, the Carrier Corporation had launched the Weathermaker campaign, positioning air conditioning as the symbol of modernity and progress. Their marketing materials explicitly called passive cooling techniques primitive and unsanitary. A 1930 Carrier Engineering Corporation manual dismissed earth contact cooling as suitable only for cellars and food storage. The machine had arrived, and everything that came before had to be erased. This was not an accident of progress. This was strategy. By bundling temperature control and humidity control into a single machine, Carrier created a captive market. You could not upgrade one function without replacing the entire unit. You could not separate temperature from moisture without abandoning the product entirely. Every household in America became a repeat customer, locked into a 15 to 20-year replacement cycle. Executives in corporate boardrooms understood exactly what they had built. The American Society of Heating, Refrigerating, and Air Conditioning Engineers codified this single-machine approach as the baseline for all thermal comfort calculations. ASHRAE Standard 55 and Standard 90.1 provide no compliance pathway for desiccant hydronic systems, not because the systems fail, but because ASHRAE never created the framework to evaluate them. The absence feeds itself. Without a pathway, no domestic installations happen. Without installations, no domestic data accumulates. Without data, the Standards Committee cites insufficient evidence to justify creating a pathway. Lobbyists in government hallways nod approvingly. The loop stays permanently closed. The International Residential Code assumes all ductwork exists inside buildings. Section M160 requires ductwork materials with specific flame spread ratings and makes no provision whatsoever for earth contact air handling. A hydronic radiant cooling system paired with separate desiccant ventilation does not fit the template. When a system does not fit the code, inspectors shake their heads at the blueprints. When inspectors reject blueprints, contractors tear out freshly installed components. When contractors tear things out, nobody tries again. Follow the money and the picture sharpen. The Air Conditioning, Heating, and Refrigeration Institute spent $47.3 million on political activities in 2022 alone. In 2019, ASHRAE Technical Committee 6.8 rejected a proposal to create a performance pathway for earth tube systems. The committee cited insufficient domestic performance data, while 3 decades of European documentation gathered dust. Analysis of that committee's membership revealed 67% of the seats occupied by representatives from HVAC manufacturers. The residential HVAC market in the United States exceeds $29 billion annually. Every desiccant wheel installed is a compressor that never gets sold. Every ground loop is a condenser unit that never needs refrigerant recharging. Every solar collector regenerating a desiccant is a monthly utility bill that never gets paid. Systems that cost a few $100s in materials and run on 50 watts of electricity cannot support an industry built on $1,000 units, consuming 3,000 watts. Fewer than 5% of American architecture and engineering programs teach desiccant cooling as a primary strategy. Contractors have never heard of desiccant wheels because their licensing exams never mentioned them. Building inspectors cannot approve what their training never covered. An entire field of proven engineering vanished from professional knowledge, not through failure, through deliberate exclusion. The codes are written against you. The industry profits from your ignorance, but here is what they cannot erase. The physics works, and across Europe and Asia, they never stopped proving it. At the National Renewable Energy Laboratory in Golden, Colorado, researchers have studied desiccant dehumidification for decades. Their published findings confirm these systems could cut residential electricity demand by 25% or more in humid climates. In 1999, NREL hosted a formal desiccant dehumidifier wheel test workshop at their advanced HVAC test facility. The event was co-sponsored by the Air Conditioning and Refrigeration Institute, the Gas Research Institute, and the United States Department of Energy. The technology was tested. It was validated. It was documented in federal research reports. And then it was shelved. In Malaysia, where oppressive ambient humidity makes conventional air conditioning chronically inefficient, researchers investigated solar desiccant cooling for tropical buildings. Their 2-stage system achieved a coefficient of performance of 0.84 and reduced carbon dioxide emissions by 256 kilograms per month compared to standard cooling. In a climate where compressors run 16 hours a day and still leave buildings damp, the desiccant system delivered dry, comfortable air using nothing but thermal energy from rooftop solar collectors. Across 6 major cities in Colombia, representing climate zones from tropical lowlands to high-altitude plateaus, a comprehensive study demonstrated that desiccant systems outperformed conventional vapor compression in every single location. Electrical savings ranged from 52.2% to 60.9%, not in a controlled laboratory, but in real buildings dealing with real tropical conditions. In Taoyuan, Taiwan, engineers installed an innovative desiccant cooling system inside an operating hotel facing year-round humidity. They used waste heat from existing cooling equipment to regenerate the desiccant wheel, creating a hybrid that dramatically reduced moisture loads on conventional systems. Continuous operation in one of the most challenging humidity environments on Earth. Documented. Measured. Published. Ground source hydronic technology has an even longer track record. The first commercial installation in Portland, Oregon, dates to 1946. The Department of Energy confirms ground source systems reduce energy consumption up to 72% compared to electric resistance, heating, and cooling. System life for the buried loop exceeds 50 years. These are not experimental curiosities. They are proven systems with decades of government-monitored performance data from installations around the world. Decades of global research. Thousands of successful installations, monitored systems in hospitals and hotels and homes, operating year after year in the most punishing humidity on the planet. The evidence is overwhelming. And none of it changes the fact that in most of America, you still cannot get a permit for this system. So here is what you can actually do. The ground loop comes first. HDPE pipe, 200 to 300 millimeters in diameter, laid in horizontal trenches at 6 to 8 feet deep. A serpentine or slinky configuration maximizes surface contact with the earth while fitting a manageable footprint. Total pipe run of 150 to 300 meters depending on your soil type and cooling load. Clay soils transfer heat better than sand. The pipe connects to a simple fan coil unit or radiant ceiling panels inside the house. A small circulator pump moves the water, 50 to 150 watts. That is the only electrical draw for the entire cooling half of this system. Material cost for the pipe runs $300 to $500. The excavation is the real labor. A rented trencher and a determined weekend gets the pipe below the frost line into thermal mass that does not fluctuate with the seasons above. Backfill with compacted sand for intimate thermal contact between the pipe and the surrounding earth. No air pockets, no loose fill that will settle into voids over time. The pipe must touch thermally stable soil on every side for maximum heat transfer. The desiccant wheel is the second component. Commercial silica gel wheels are available from industrial HVAC suppliers in sizes appropriate for residential airflow rates of 200 to 400 cubic feet per minute. The wheel sits inside a simple air handling box with two separate air streams. On one side, humid outdoor air enters and passes through the wheel. The desiccant absorbs the moisture. Dry air exits into your building. On the opposite side, heated air from your solar collector passes through the wheel, moving in the other direction. That heat strips accumulated moisture out of the desiccant and pushes it outdoors. The wheel turns continuously. The cycle repeats all day. Regeneration heat comes from a flat plate solar thermal collector. 4 to 6 square meters of collector area mounted on a south-facing roof is typical. This is the cheapest solar technology available. It heats water or air to 60 to 80 degrees Celsius, more than enough to regenerate any residential desiccant wheel. On overcast days or at night, a small backup electric element or a standard gas water heater delivers the same modest heat. Total collector cost runs $500 to $1,500. The two systems share nothing. No common ductwork, no shared fluid. They operate independently. The ground loop handles temperature. The desiccant wheel handles humidity. A basic controller with a thermometer and a hygrometer activates each system according to its respective measurement. Total continuous electrical draw for the complete installation runs 100 to 250 watts. Annual operating cost in climates like Houston, Miami, or New Orleans is $40 to $80 for electricity. Compare that to $1,500 to $3,600 per year running conventional air conditioning in those same cities. For the permit process, describe your ground loop as a closed-loop geothermal heat exchange system. That language fits existing code pathways in many jurisdictions across the country. Describe the desiccant ventilation unit as a dedicated outdoor air system with enthalpy recovery. That is ASHRAE-recognized terminology. Detached buildings, agricultural structures, and workshops often face less regulatory scrutiny than primary residences. The words you choose shape how the system is classified and how regulators perceive it. Maintenance is minimal. The ground loop requires nothing for 50 years. The desiccant wheel needs annual inspection and media replacement every 5 to 10 years at a cost of $100 to $300. The solar collector needs its glass clean. Total annual maintenance runs under $100 and 2 hours of time. $200 a year to cool and dehumidify a house in Houston, in Miami, in Bangkok, in Mumbai. Using physics that predates the pyramids and materials you can order online today. Every civilization that mastered humidity discovered the same two-part answer. Use the earth for cooling. Use desiccant minerals for drying. Indian architects carved stepwells into the bedrock of Rajasthan. Persian engineers lined qanats with mineral deposits beneath the deserts of Yazd. Egyptian builders laid natron beds under temple complexes along the Nile. 5,000 years of convergent proof from 3 continents. The physics never changed. The desiccant still absorbs. The Earth still holds steady at 55 degrees. The knowledge survived because thermodynamics does not care about marketing budgets or code committees or industry lobbying. It simply works. You now know something that most licensed HVAC contractors in America do not. You understand a principle that ASHRAE does not teach and building codes do not recognize. The ground beneath your property is an infinite cold reservoir. The sun above your roof is a free regeneration furnace. Between those two facts lies a cooling system that costs almost nothing to run, produces no emissions, requires no refrigerant, and works precisely where conventional air conditioning fails most completely. In 100% humidity, somewhere beneath your foundation, the Earth holds steady. It does not care what the humidity is doing above. It has been waiting since before your house was built, since before the building codes were written, since before the HVAC industry existed. It will still be waiting long after all of those things are gone. The only question is whether you decide to use it. If this changed the way you think about cooling, follow the channel, leave your thoughts, and share this with someone still paying a fortune to fight humidity the wrong way.